In this lecture, we're going to focus on the development of the discrete time transfer function. This being formed via the zero order hold and also the continuous time transfer function. So you can see the table of contents. So we're going to go over, just give you an introduction, then the tables of transforms, steps to a discretise transfer function, then finally summary and next steps. So after this, you should be able to understand the use of the zero hold to discretize a continuous time transfer function and understand the use of the tables of transform to transfer between different modeling domains, and also finally to understand the numerical steps for discretizing a continuous time transfer function. So you've seen this in the previous two videos, so I'm not going to spend too much time here. If you want a bit more of a detailed overview of this, see the previous videos. But this is your sampled data control system, where we've got a mixture of continuous signals, which are in the blue, and discrete time signals, which are in the red. Because we're now looking at digital control, what we work in now in terms of computers is discrete time events, and hence the information that we need to provide the microcontroller, the controller, is in discrete time. And in terms of a lot of sensors tend to be continuous, actuators tend to be continuous, so we have kind of the sample switch, which will sample your continuous signal, and the zero order hold, which will effectively hold your discrete time signal for TS seconds, converting it from this discrete time signal to this continuous time. So it's effectively holding the control action here, the control output U star, for TS seconds. So this could be holding some sort of voltage to a DC motor. And the amount of information provided to the controller at this sample switch very much depends on the sample switch, and how long the control action is held for also relies on the sampling interval. So in terms of discretizing a system's model, we make use of the zero order hold. So in the previous video, we looked at G subscript ZOH, so the zero order hold of S. So we had continuous time zero order hold, continuous time system that we've seen on previous course. And to get the discrete model of that, the discrete time model, we undertake the Z transformation of that. And you can see here your continuous time zero order hold given here, and then this represented on this block diagram over here. And you can see the signals that you used to see. So in the previous video, we discretized the numerator of the zero order hold. So this term here, we discretized that, and we ended up with Z minus 1 over Z. Hence why, if you look in here, the Z transform, you can see now to the left of it is the transformed numerator of the zero order hold. However, because we didn't discretize, you can see here the denominator S here, we're left with this 1 over S term here multiplied by G of S. So don't forget that 1 over S there. Alternatively, you could do G of S over S. Okay, because effectively that S there is just multiplying by G of S, and hence you're getting this. So the final stage that we need to do is we need to do the Z transformation of the continuous time system model, so G of S and of S. And once we get a discrete time system model, this is effectively what we'll get, as you can see down here. So we'll have G of Z, and then we'll have U of K, so our sampled input, and then Y of K, which is effectively our discrete time or sampled output. So you can see we're going from a continuous model here, so continuous time, to discrete time. And why we're doing that is because what we want is, because now we're working in discrete time with systems modeling, what we want is we want a G of Z. Okay, in terms of theory, we can't mix domains, we can't mix G of S with, when we get onto control, we can't have a discrete time controller with a continuous time system. So we need a discrete time representation of the model. Okay, because in theory, like I said, we can't mix the modeling domains. In simulation, in Simulink, you can actually get away with mixing up, so you can have a G of S for the system, and then you can have a discrete time, for example, PID controller, so you can get away with mixing up modeling domains. Because effectively Simulink will do the mathematics for you in the background. It'll discretize your continuous time controller for you. But in theory, we want to be modeling in one domain. So tables of transform. So this enables us to transform from one domain to the other. So you've seen previously, you should have seen how to go from or go vice versa, from that way to that way, or that way to that way, whether you're doing transformation. So if you look at 14 and 15, this here are our derivatives, so our rate of change, and we can undertake the Laplace transformation to effectively get the equivalent representation of that. So you should recognise that if you've covered the continuous time. Alternatively, we can also do inverse Laplace to go back to the time domain. So what we're interested in now is, because we are working in this row, this column's the final column, because we're looking at discrete time systems now, the representation of digital control systems. And what I've got here is some examples. So we look at row 5 here, and then we've got this transfer function here in continuous time, 1 over s plus 2. Okay, so it's effectively that's that. 1 over s plus alpha, where alpha is 2. That transforms into this here, where you can see effectively that alpha here just becomes 2. Okay, so you can see there, and that just becomes this transformation here, z over z minus e to the minus 2 multiplied by ts, where ts is the sample interval. Okay, nice and straightforward. So we've transformed from one domain to the other. Again, row 6, if we look at row 6 here, we've got 5 over s, and then brackets s plus 5, where effectively the alpha term here, I'll just highlight that, is 5, and this is 5. And then the transformation is given by this equation here. So again, where alpha here just becomes 5, and alpha here becomes 5, and hence this transformation that you can see here. Okay, nice and straightforward. Then if we look at this one here, where we've got 1 over s plus 1 over s, and then in brackets s plus 2, then in brackets s plus 3, you can see when you look down this column here, there's no standard. Well, there's nothing that matches that. You've got one that looks similar to here, but then it's missing the s. So in terms of the tables, there's nothing standing in there for us to transform from one to the other. So what we need to use is partial fractions to be able to undertake that. So this then leads me on to the steps to discretize a transfer function. So I'll give you an introduction into the tables, which we're going to be using for these steps. But the steps are, as I've just mentioned, the use of partial fractions. So when we have a transfer function in continuous time that we can't directly use the tables, we need to break it down into these partial fractions. So you've seen partial fractions hopefully before. So we've got real roots, the transformation, 2 equal real roots, the partial fractions this, 2 equal real roots, partial fractions that, and real pole and 2 complex poles, the partial fractions becomes that. And what we're trying to do is effectively determine what the unknown coefficients are. So where a, b, and c are unknown coefficients. Once we work out what those coefficients are, then we can then directly use the tables. And you'll see that in the example coming up. 2 is then we use the table of transforms, because once we get into the form of the partial fractions that we're happy with, we then use the transformations to convert from the continuous time domain to the discrete time domain. And then what we want to form is a common denominator, because what we are likely going to end up with is we're going to end up with maybe 2 or 3 partial fractions, and then what we want to do then is form a common denominator so that we've got one transfer, well, we've effectively got a transfer function. And then finally multiply the zero to hold numerator that we discretized earlier by effectively what the transformation is that we've just undertaken. So just multiply that. So what I have now is an example to run you through those steps. So a sampled data control system is designed where the sampling interval Ts is equal to 1, and the open loop system transfer function is given by this. So here you've got your second order continuous time transfer function. And the zero to hold of the transfer function is given by this. So you've seen this in the previous video, and you've seen also by making use of g of z is equal to z minus 1 over z, the z transformation of gs over z, s. And again, you've seen that. Show that the z transform of open loop system is given by this. So what we effectively need to do is we need to, g of s multiply by that s there. Then we need to go for the steps that I've just shown you to effectively end up at this transfer function. I've also told you here what the partial fractions are that you need. So you can see there a over s plus b over s was 2 plus c over s plus 3. So step 1, partial fractions. So let's use the partial fractions. So what we want to do to begin with is, well, you can see here I've this transfer function here. What you need to make sure you're aware of, as I just said, g of s is here, but you need to make sure that this transformation here is g of s and also this s here. So you effectively got an s term that's multiplying by this. So that's why you're going to end up with this s term here, because it's here. Okay, so just be aware of that. So if we're looking at that, that's where that s terms come from. That's why you end up with that partial fraction. So if we cross multiply the above by s plus 2, s plus 3, okay, so we cross multiply this side and this side, what we're obviously going to end up with, that's going to cancel that, so we're going to end up with 12. Then we're going to end up with a, okay, that, let me just think, that, if I'm looking at this, yeah, they end up at 12. And then this over this, you're going to, the s and the s are going to cancel, so you're going to do with a, we're going to do s plus 2, s plus 3, and then obviously if you multiply that out, you'll get that. Plus then, cross multiply that by that, you're going to end up with b, s, and then the s plus 2 are going to cancel, s plus 2, so you're going to do s plus 3. And then here, cross multiply that with that, you're going to end up with CS, and then the s plus 3 are going to cancel, so you're going to do s plus 2. Then if the method I'm going to use now is equating the coefficients, you could use the cover-up rule though, but I'm using equating the coefficients. So S0, so if we're looking at this here, ask ourselves, what coefficients here are effectively where there's no 0? So there's no, sorry, not any 0 when there's no s, sorry. So here you can look, 12, okay, there's no s, so yep. Then we look here, so A, okay, 6, A6, yep. Therefore, well, I'll just go across, because there's an s term here multiplying through, there's an s term here multiplying through, there's not going to be any single coefficient on its own. So that means that 12 is equal to 6a, therefore a is equal to 2. So we've already got a. S, where there's just an s term, so obviously there's no s term here, so we're just going to put 0. Then if we look in here, there's an s term here, so we're going to end up with 5a. And in terms of here, this s is obviously going to multiply by that, so you're going to end up with 3b. And then here, cs, that's going to end up there, so you're going to end up with 2c. So there we've got that. And then if we're looking at s squared terms, so there's obviously no s squared term on this side. There's an s squared term here. This is going to multiply through, so you're going to have an s squared term there, and that's going to multiply, so you're going to have an s squared term there. The coefficients are there for just 1, so it's going to equal a plus b plus c. Okay, so we end up with another expression. What we want to do now is subtract s squared from s1. So what I'm going to do is multiply this here by 2. That effectively will enable me to get rid of the c terms. So what I've then done is, you'll see is obviously I've multiplied this by 2. And then I'm going to subtract this from S1. And then what I end up with is, obviously I'll end up with 2a, so I'm going to end up with 3a, because if 2a multiplied by 5a is going to be 2a. Then, because then this is 2b, subtract that, and then with b, and then 2c, take away 2c, is obviously going to cancel. So now what I can do, because I know a, I know that a was 2, because I worked it out up here, I can substitute that in. So that's going to be 0 is equal to 3 multiplied by 2, which is going to be 6. Take away b. Therefore, because this is going to be equal to 0, I know that b is going to be equal to minus 6. So I've got a, b, and c. Then if I substitute in the previous equation, substitute it into the previous equation, so I can just substitute into this original equation, where a is 2, b is minus 6, then c is a value, and you know this whole thing is equal to 0. Therefore, I know that c must equal to 4. Okay? 2 take away 6 plus 4, that's going to give me 0. Okay, so now I've got a, b, and c. So now I've got my partial fraction form given here. So what this then enables me to do then is move on to step 2, where I can use rows 3 with ID 3 and 5 in the tables of transform. So I can see straight away 2 over s here, so have a look up here, relates to this where I've got 1 over s. So that transformation, what I can do is well, I can transfer that to z over z minus 1, and in our case we've got the value on the top being 2, so I can effectively just move that outside the brackets as I've done so there. Then likewise with these ones, so you can see I've got minus 6 over s plus 2. So 1 over s plus alpha, it transforms into this, and you can see that again I'm just going to move the 6 here outside the brackets, and then you can see in our case there's 2 here, this alpha just transforms to that, so you can see 2 there. And then exactly the same with this final one, 4 over s plus 3. Okay, 1 over s plus alpha. Again, move the 4 outside. So I've got 1 over alpha, 1 over alpha, where alpha's 3 in this case. So it's going to end up just being that value there is going to be 3. And that's there is our discrete time representation of these partial fractions. Then let's just take z out as a common factor. So you can see on the numerator I've got z, z, and z. So what I can do is just move that out as a common factor. So 2z, and then brackets, and then that should just be 1 over z minus 1. And then there, because obviously I've got a 2 multiplying through, that's now going to become 3 because it's 6 there. This is going to become 2 because I've got 4 there. So if we recall from the previous slide, this equation, what we want to do in step 3 is form a common denominator. So what I'm effectively going to do is just take these these denominators from these partial fractions and put them here. And to mathematically equate that, what I'm then going to do is, well, I've got this common thing, and to make that this mathematically equivalent to that, you can perhaps see this, but this part here, if this was over this, what I would end up with, that would count, this bit would, and this bit would cancel, that bit and that bit would cancel, so I just end up with 1 over z minus 1, which is what I've got there. And then likewise with this part, so if I'm looking at this here, so this over this, so that and that would cancel, this and this would cancel, so it'd end up with just minus 3 over z minus e to the power of minus 2ts. And exactly the same with this final part here. So this over this, this and this would cancel, this and this would cancel, so it'd end up with then just plus 2 over z minus e to the minus 3ts. So there I've formed my common denominator. Then what I want to do is just basically go through some steps here of just simplifying. So step 4 is really just to simplify the transfer function and to multiply it by the zero order hold. So what I'm going to do here initially is just multiply these exponential terms. And just recall that when you multiply two exponential terms, so e to the n multiplied by e to the m is equal to e to n plus m. So you can see what I've done there is just effectively multiply out the exponential terms. And what you should notice in the next step is you should get the z squared terms also cancel out, because you've got a z squared term here, you've got a z squared term here, you've got a z squared term here. This one's z squared, take away 3z squared plus 2z squared. So you should notice that they all cancel out, and this should be a step that you notice all the time. Then I'm just going to then further expand this out, further expand the equation out, the transfer function, you can see that. And then I'm going to rearrange to effectively move this z minus 1 outside the brackets, as you can see here. These aren't necessarily the steps, you can take different steps and explore the maths, look at the maths and see what I've done there. So what I've done in this final here is, you can see these TS's here. Okay, this is our sample interval. Okay, they're everywhere. You can see what I've done then is substituted in 1. I've used my calculator, and then I've ended up with this equation here. So 2z over z minus 1, and then this here that looks like, where you got the numerator and denominator, and then this outside. So now if I multiply this by my zero to hold numerator, so if you recall that was z minus 1 over z, what I get is this. And you straight away will notice that's going to cancel with that. That z then is going to cancel with that. And you're effectively just going to end up with 2 multiplying by the numerator there, as you can see here. And then we can further simplify this. And this here is our discrete time transfer function, g of z. And that's what we saw on the first slide. So we've gone through the transformation now, and we've ended up with the discrete time transfer function, as you can see here. So we've done g of z, we had the numerator of the zero to hold, and then we've done the z transformation of g of s over s, g of s for a given transfer function that we were given with a sampling interval of 1. So in summary, following the 4 main steps, the zero to hold has been used to obtain a discrete time transfer function. To understand the discretization, the tables of transforms have been used. And just be aware, in practice, the zero to hold would actually be located on the microcontroller. But in theory, we couple up the zero to hold with g of s to then form a discrete trans function. So the next steps, what I'm going to detail in the next step is detail the mathematical forms of various inputs and references used for open loop and closed loop systems, and also the discretization of a continuous time system using MATLAB when subject to a unit step input to attain a system output. So thank you for listening. If you've got any questions, please email me.